Hi, in this video we are going to discuss the over an example the properties of the Fourier series coefficients of a real valued signal. Now first let us define the periodic signal. We start with the finite duration signal P of t, which is an exponential function over the interval from 0 to 1, and it is equal to, over that interval, it is equal to a e to minus t. Therefore, this point here, the value of the function at that point is a e to minus 1. So P of t is equal to a e to minus t for t between 0 and 1 and 0 elsewhere. Okay, so we have this finite duration signal. Now we obtain a periodic signal by the periodic extension of this signal as follows. Let us define x of t as m from minus infinity to plus infinity, p of t minus 2m. So we have the periodic extension with a period, fundamental period, t0 equal to 2. So x of t is a periodic with fundamental period t0 equal to 2. Therefore, omega 0 is equal to 2 pi over t0, and it is equal to pi. Okay, so we have this periodic signal. Therefore, it will have the Fourier series representation, k running from minus infinity to plus infinity, ak e to j k, omega 0 is pi, e to j k pi t. In fact, we can plot x of t as follows. So from 0 to 1, it will be the exponential function, and then between 2 and 3, again we have the same exponential function. Okay, so we have such a periodic signal, which is our x of t. Okay. Now, how can we evaluate ak? ak is, remember, 1 over t0. We integrate over a period. Let us integrate from 0 to t0, for instance. X of t e to minus jk, well, omega 0 here is 2, pi, not 2 is t0, k pi t, integrated with respect to t. Now t0 is 2, and we integrate from 0 to 2 x of t e to minus j k pi t. Okay, but over the period from 0 to 1, x of t is equal to a e to minus t. From 1 to 2, it is equal to 0. Therefore, we only integrate from 0 to 1, e to minus j k pi t integrated with respect to t. Okay, we can combine these two exponential functions as e to minus 1 plus j k pi t, and then integrate. Okay, a is constant, so it can be taken outside. We have a over 2, 1 over minus 1 plus jk pi e2 minus 1 plus jk pi t evaluated at integration limits 0 and 1. Okay, so to get rid of this minus sign, first evaluate at 0. So we have a over 2, okay, and also 1 over 1 plus jk pi is the common term. So we get rid of the minus sign, and that's why we evaluate at 0 first and then at 1. So at 0, this is equal to 1 minus e2 minus 1 plus jk pi. Okay. Now, let us look at this exponential. Okay, let me write it over there. So we have a over 2, 1 plus j k pi. Then we have 1 minus e2 minus 1. And we have e2 minus jk pi. But e2 minus jk pi is e2 minus j pi raised to the power k. But e2 minus j pi is equal to minus 1. So this is equal to minus 1 raised to the power k. So we have a over 2, 1 plus jk pi, 1 minus e2 minus 1, and minus 1 because e2 minus j pi is equal to minus 1 and raised to the power k. So this is the expression for ak, where k is running from minus infinity to plus infinity. So these are the Fourier coefficients. Now, remember that for real valued signals, the Fourier coefficients satisfy certain relationships. For instance, ak is equal to a minus k conjugate. That means for real valued periodic signals, you always have positive frequency components and their negative frequency counterparts. Now, if we look at this expression, it is clear that that condition is satisfied. A minus k is, now this k here is replaced by minus k. And if we take the conjugate, here the only complex quantity is this term in the denominator. And in the complex conjugate, we have minus j instead of j. So minus j and minus k will, the product will be again jk. And we obtain, we verify, in other words, the expression a minus k equal to ak conjugate, or ak conjugate is equal to a minus k. Now, we can also observe the following. We can look at the even and odd parts of x of t. The even and odd parts of x of t are also periodic functions with the same fundamental period, and therefore they also have Fourier series representations. So how do we evaluate the coefficients, Fourier series coefficients? So let us now look at this problem. Okay, now we have evaluated the Fourier series coefficients of our signal x of t as ak equal to a over 2 1 plus jk pi multiplied by 1 minus e to minus 1 minus 1 to the power k. Okay, now remember that the even part of x of t is obtained by x of t plus x of minus t divided by 2, and the odd part, okay, maybe it is better to write this as x even and x odd. The odd part is x of t minus x of minus t divided by 2. Okay, now x of t was, let us discuss this graphically. X of t is remember the periodic signal with period 2. So we have this exponential signal like this, and we have the periodic repetition of this. Now let us draw the graph of x of minus t. X of minus t will be also a periodic signal. So we have here, let us draw the signal for over the interval from minus 1 to 0. It is this. Remember that we obtain x of minus t from x of t by means of a reflection with respect to the vertical axis. Then from 0 to 1 we have 0, and then from 1 to 2 we have again the same exponential function, and etc. So we have this periodic signal which represents x of minus t. So when we add them up, we obtain the even part. So from these two, we obtain, by means of the first formula, the even part of x of t, x even of t, as the following signal. From 0 to 1, and then from 1 to 2 we have this part, and then from 1 to 2 to 3, and etc. So we have, this is the even part of the signal. Remember, x of t over the interval from 0 to 1, it is equal to a e to minus t. For x of minus t, from minus 1 to 0, it is equal to a e to t, because t in x of t is replaced by minus t here. So we have this even part. So we have these exponential decays, and then again an exponential decay, exponential behavior. Okay, we have such a signal. And for the odd part, the odd part of t, and by the way, since we have the factor 1 over 2, here this value here is a, and also here a. So in this case, the value here is a over 2. Now for the odd part, we have x of t minus x of minus t divided by 2. So the odd signal will be, odd part of the signal will be, again we have a over 2 over there, between minus 1 and 0, we will have this function. From 1 to 2, again we are going to have the same behavior. So we will have such a signal as the odd part. 2 to 3, and etc. We have the periodic extension. Now, in fact, we know that x of t is equal to the sum of its even part and odd part. So, from AK, how can we obtain the Fourier coefficients of, for example, the even part? Okay, let us do it here. X even of t will also be periodic with Fourier series coefficients equal to a real part of AK, and the odd part of t will have the Fourier series coefficients j times imaginary part of AK. Okay, this is valid, of course, only for real valued signals. Now let us calculate these coefficients. So the even part of t. Okay, first of all, let me write ak here, or let us look at this expression of ak over there at the beginning of the page. The only complex quantity here is in the denominator, which is 1 plus j k pi. Now, we can multiply ak by the we can multiply and divide ak by the conjugate of 1 plus j k pi. So ak will become a over 2. Then we have 1 minus j k pi divided by 1 plus j k pi multiplied by 1 minus j k pi, which is 1 plus k pi squared. And then we have 1 minus e to minus 1 to the power k. Okay, so the even part of x of t will have the Fourier series coefficients given by the real part of ak, which is a over 2 1 plus k pi square 1 minus e to minus 1 to the power k. Okay, so this is the Fourier series coefficients corresponding to the even part of x of t. And for the odd part, we have j times the imaginary part. The imaginary part can be obtained from this expression as well. So it is minus j a k pi divided by 1 plus k pi square 1 minus e to minus 1 to the power k. Okay, sorry. So these are the Fourier series coefficients of the even and odd part. Now we observe something interesting. In fact, if we look at the behavior of the Fourier series coefficients for larger values of k, as you see in the Fourier series coefficients of the even part, we have a behavior in the form 1 over k square for larger values of k. But for the odd part, we have that behavior is in the form 1 over k. The magnitude is proportional to 1 over k for larger values of k in the odd part, but in the even part it is 1 over k square. So why is this so? Now we look at the signals, the even part and the odd part. As you see in the odd part of the signal, and as well as the signal itself, has discontinuities. A sudden jump from one value to another value. But in the even part of the signal is continuous. So it is a smoother function. And this property is also present in the behavior of the Fourier series coefficients. The Fourier series coefficients of the even part decay, in other words, more rapidly as k tends to infinity than the Fourier series coefficients of the original signal, which has discontinuities, and also the odd part of the signal, which is again which contains discontinuities or jumps from one value to another value. Remember, this observation is discussed in detail in the video related to the application of Riemann-Lebesgue lemma in Fourier series representations. There should be a 2 here as well. And we should close the brackets here. Okay, so these are the coefficients for the even part and for the odd part. Now, it is also possible to observe the following. If you express the Fourier series in trigonometric form, the even part of the signal will be represented in terms of a cosine series, because the cosine signals are even, and the odd part will be represented in terms of a sine series. So this is also another observation related to our example in particular, and for real value signals in general. Okay, thanks for watching.